Hey, welcome back to another episode of the Vit Nerd, and I have a special guest today, Paul Krizak.
How you doing?
Good. I'm good. You're good?
I'm good.
Good. So, Paul, a little bit of background. Well, we've got you, and we've got you with the Odyssey.
The Odyssey computer, yes.
Right. Not to be confused with the Magnavox Odyssey, just like not to be confused with this thing and that thing and whatever. Multiple names are used. The Odyssey, it's your Odyssey.
That's right. Yeah, I've been building this for a decade. I started it in earnest around COVID, around 2018, 2019. But it's been scrolling around in my head for a long time. And so when it came time to give it a formal name, I called it the Odyssey, the Wire Wrap Odyssey.
Yeah. Well, that's the backside here, and we'll show some photos of that as well. And you've shown this at VCF SoCal before.
That's right.
Here. And are you able to make 2026?
I expect to, yeah.
Okay, cool. So if you haven't seen it yet in person, perhaps this coming February, but you can see it here today. And what this is you created a computer.
That's right.
Right? Out of discrete components. There is no actual CPU chip in here.
Correct.
What you've done is you created, a CPU chip, if you say a 6502 and you scraped off the silicon and you got down, you always see those little pictures where it's like little islands with the wires and the line. You're like, those must be things that do things. That is this right here.
Right.
This is the CPU, this middle board. Is there anything else on this middle board that isn't the CPU?
So the CPU is basically from this side all the way over to about right here. And then I have some peripherals, the timer and the UART and stuff here, and then there's additional peripherals down here. But the thing that you would traditionally think of, like the Z80 or the 6502 or the 8086 or something, chip, the thing that's the CPU, is actually this part of the board right there.
Okay, so you're not using a CPU per se, off-the-shelf stock CPU. You created your own.
Correct.
Which means you had to add the address bus and the registers and the interrupt handling and everything with that.
I even implemented the whole instruction set myself. So a lot of people have built homebrew computers like this, and they've used an existing instruction set. They'll re-implement the 6502 instruction set or the MIPS instruction set, which can make things a lot easier because you can take off-the-shelf assembly code and you can run it on your homebrew computer. I went the harder direction and I made my own instruction set. So everything in here is completely custom. This isn't based on MIPS or x86 or 6502 assembly or anything. Everything's completely custom.
Okay. Well, we're going to get into it, why Paul did this, what is in here, what can it do right now. The big question first, though, can it run Doom?
It cannot run Doom, but
okay,
I do expect
thanks for watching. It's been a fun episode, and we'll catch you next time. Okay, so I've got a couple questions, at least, right? You said 2020 or so, the pandemic began. If anybody remembers that, you got really into this.
Right.
But that was only 5 years ago, and you've been doing this for a decade.
Right.
It's not that it took you this long, per se. You did piece by piece.
That's
you didn't just go in your garage and I'm going to wire all this together and there it goes. This was an odyssey. I mean, I'm using that word again, right?
Yeah.
And you started with the video board, which is up here.
Right. But even before that, I wasn't even sure how to build it. I came out of college in 2005 and I had taken as one of my electives a computer design class. So I had learned in school how to build a microprocessor and the function of the registers and the program counter and the interrupt handler, and I knew conceptually how all that stuff worked, and I had this itch in the back of my mind that I wanted to build something like that with my own two hands, not just doing it in Verilog, not simulating it.
And I'm going to pause you there because I think you kind of hit the nail on the head there, where I think the rest of us come in. We all, if you're watching this video, you know how this works, right? I mean, 8-bit computers, we all started, it's just like if you got in the cars, carburetors and all that nobody knows anymore. So we all know those little things, but that itch, you had that itch. I've got the itch to play with him and make him do things, and you got the itch like, well, I guess it might be time to bring up Ben Eater, right?
Right.
If you've watched Ben Eater, you know. If you haven't, go YouTube Ben Eater. Great.
Fantastic.
Yeah. The chips, the breadboarding, the making things happen, the instructions and so forth. So that's the kind of thing you got into. And then you had the itch, you can build your own.
Right.
We've all had that itch, but never jumped on it. But you did. So you started close to whatever, 10 years ago. Why start with the video board?
So I started with the video board because I had started with something like this. So this is point-to-point wiring. This was one of my early prototype boards. So this is a clock and reset board. And I did it on proto board, and I did point-to-point soldering on here. And this took me, this one board, maybe a week to finish. Like, it was a complicated, difficult board, and at the end, all it could do was a clock signal and a reset signal. And so that got rather frustrating, and I would kind of put it away. And then later...
Okay, this is, if I went to do this right now, this is 2 or 3 months, I would say. But, yeah, okay.
So, that... And I thought, all right, well, I'm just gonna keep pressing at it. So I'm gonna build this. And so this was the second board that I built. And again, this is a proto board, and this was the program counter. And it's got a few chips that are missing because I had to steal them for something else.
Yeah.
But you can see again, this was point-to-point soldering with just soldered joints here. And then I tried to do a little bit more efficient, where I started making my own PCBs. And again, this whole process it worked, but it's very inefficient. It's not very dense, and it took me forever to do that. And so I still had this itch in the back of my head, but as I tried to work on it, I just didn't feel like I was making good progress. And here again, I made another board here on this product called Bus Board, and then I put these VeroBoard connectors on the end, and then I made a backplane that these would connect into, again, using busboard. And again, this helped make things go faster, but every time I'd sit down to work on it, I felt like I was just toiling. I wasn't really getting anything fun or useful or entertaining at the other end of the spectrum. And so I saw the Ben Eater video about you can make your own video card on a breadboard. And I thought, well, I'm going to need a video card at some point for my computer, so why don't I just start with that? Instead of working on this stuff that's just making a clock tick or making a reset signal or something, let me start with something that is interesting enough and that actually does something at the end. And so I watched his video, and I had some ideas, and I drew out a bunch of schematics of how I'd make my video card work. And then I started out on a breadboard. I got about halfway through it, and then connections kept coming loose, and it was just not very reliable. And then I saw a Hackaday video from Bill Hurd, who's one of the designers of the Commodores.
Oh yeah, he had this up here.
That's right. So he did a video about wire wrapping. And it was more of a historical tape, back in the day, this is how we did wire wrapping. And I'm looking at that going, well, that's exactly what I need to do. I need to be doing this on a prototyping board, but I don't want to be soldering things, and I don't want to be using the friction of a breadboard. And wire wrap was right in the middle of what I needed. You're able to make changes on the fly. You can make edits. If you do something wrong, you can pull the wire off and do it again. And more importantly, unlike a PCB, which would be great if you do everything on a PCB, you don't have to plan it all out all at once. So I could design something on paper, and then I could work on a little bit just by hooking up some wires. I could test iteratively, so I could hook up a little bit at a time. I do the horizontal clock counter, and then I could hook it up to my logic analyzer and see that it worked, and then I do the vertical timer, and then I do the character generator, and then I do the color generator, and just a little piece at a time. And after about a month of work, I had a video card, and that's this board up here at the top. So everything on this board is the video card and the main memory. So I implemented in forethought, I used a modern memory. So that's a 32 kilobyte IDT dual port RAM, which is not something you would have gotten in the 70s or 80s. So this isn't supposed to be like time correct or anything, period correct. But
yeah, you've got things from the 80s, 90s, aughts,
exactly, it's a whole
10s.
mix of stuff in here. But the point of doing it with a dual port RAM was that I could get the video card fully functional and then just use something like an Arduino to write data into the memory to prove that the video card worked.
Right.
And then that was really fun. I had so much fun doing that part of the project that I realized that I had the formula down. The formula was wire wrap instead of trying to do it on PCBs or breadboards or something. And the formula was also not restraining myself to everything has to be a 7400 series part, or everything must be from something you could buy in a catalog from 1985. Like,
yeah, you wouldn't be this far.
exactly. And so I with that mindset, and this was, again, I did the video card. This was shortly after Ben Eater did that video, so I think that was 2019 that he released that video.
Okay.
That's when the real motion started, because at that point I had had about 8 years of thinking about how this might work, but just getting blocked on the implementation, on the actual getting my hands dirty and putting all the wires together. And once I got that video card done, it was full steam ahead, and I started actually building out all the stuff here, which is thousands of wire wraps to make all that work. But because I had that experience of the video card and doing it incrementally, I was able to apply those same lessons and get the CPU and the peripherals built using that same mindset of just build a little bit at a time, test it, add a little bit more, test it, add a little bit more, test it. And then if I needed to make changes, which I had to make lots of changes as I went because I made mistakes and oversights, I just go in, pull those wires off, put new wires in different places, and correct path as I go.
Mm-hmm. So now I just want to say breadboarding's not terrible. I've touched wire wrap years ago, but breadboarding pretty much. But I've done just little small system, subsystems. So if you're getting into some of the Ben Eater videos, for example, yeah, definitely use breadboarding. You don't want to wire wrap that stuff. It's simple enough on the breadboards, and even in his videos, he gets the 3 or 4 or 5 breadboards.
Correct.
And that's where you hit this limitation, where you could put like 4 or 5 chips on a breadboard, and that's about it, because you got everything plugged in, and now you got to get another breadboard. Where on here you could get those 5 chips in such a small area.
Exactly. You get so much better density.
Right, and you're able to change things. So you started with the video card, and you made it do things.
Correct.
So what was your next subsystem of this?
So the next thing I started working kind of from left to right here. So the first thing I did on the CPU board, which would be this big blue board here, is I needed a main clock. So I had the clock from the video card, which is just the pixel clock for the video signal, 640 by 480, whatever. But because I'm using a dual port RAM, I didn't have to worry about the video card being clocked at the same speed as the CPU. I could have independent clocks. And so I started with a clock unit. So the first couple rows over here are, there's a voltage controlled oscillator, a VCO. So that's a 7400 series chip that you just take a voltage and you put it into one of the pins, and one of the outputs is a square wave of a particular frequency, and you can use capacitors and stuff to change the range of that frequency. But I've got mine tuned with a potentiometer that's on the board here, so I can tune that from about 500 kilohertz up to about 6 megahertz. And so I've got a range. It's running right now at about 2 megahertz, but I got that and a reset signal. So that was like the first thing that I built. And then the next thing
on the CPU board.
On the CPU board, exactly. And then the next thing I needed to build was a program counter. So if you're familiar with CPU architecture, the program counter is kind of the central rally point for what the computer is doing at that time. So it stores the address of where you are in the program. So it can increment, it can decrement, it can load a new value, like if you're jumping to a new place in memory. And so I needed one of those in order to be able to make a program do something.
Right.
So
because that's all the CPU does, is goes to a memory address,
right,
and grabs it and runs the command. If that's what it's doing, is running the command.
Correct.
Now the command may run and do other things to addresses and so forth, and send the video and whatnot. But the CPU, if you don't have something counting what's the next memory spot,
correct,
then it doesn't know where to go.
Yeah, so there's a register, the 16-bit register that stores that value, the
Yeah.
program counter. And once I got that implemented, I implemented the blinking lights actually. So if you can see right here, these,
The LED bars?
The LED bars. So that's the little blinking lights that tells you what's going on the address bus and the data bus. When you're running at 2 megahertz, it's not super useful, but you can't have something like this without blinking lights.
Yeah, but you got a potentiometer. You can slow
I can
down,
slow it down. You can make it
can
see a
lights.
little better, and it can sometimes be useful for troubleshooting. Like if it locks up, I can see it where it stopped in memory because the address bus will be locked at that address. So once I had that, once I had a clock, once I had a program counter, and once I had a couple registers in place where I could pull data from memory, store it in a temporary register, and then like load a new address, put it on the address bus, and put that memory in another, put that data in another place in memory, I could do Hello World for the first time. So before, I just had a kind of a loose collection of components, and this was the first time I actually took an EEPROM, stuck it in an EEPROM programmer, wrote 20 lines of assembly code, compiled it, flashed it to the EEPROM, put it into the computer, and powered it up, and then my monitor showed Hello World on the top of the screen, and I went running around the living room a few times screaming that I had finally got my computer working. So there's actually a video of that, by the way. So if you go to my website, there's a video of that initial Hello World
maybe we'll
running.
put it up in the corner up here.
Yeah.
What I find two things, 1,000 things with this thing. When you say I wrote some assembly code, put it into the EEPROM, it's assembly code which just numbers.
Yeah.
But you decided what those numbers mean
Correct.
in your CPU.
That's right.
So it's not like you went and grabbed the 6502 assembly list,
Mm-hmm.
the mnemonic list of that, or Z80 or Z80.
Mm-hmm.
You created your own code.
Correct.
And is this a language only you and the Odyssey speak in this
Pretty
world?
much, yeah. And so I had to write everything.
So I'm not going to ask AI to write a program for this, right? It won't
That's
know.
right. It won't know. It
Yeah.
doesn't have any context because I actually had to write everything from the ground up. I had to write the assembler myself.
Mm-hmm.
And so it's written in Python because I'm familiar with Python. But
And your day job is a Linux administrator.
right. I mean, my day job is writing glue code and automation code for Kubernetes deployments on Linux. So
Yeah.
I'm familiar with writing code. I'm a computer science major.
So all this makes sense now.
Yes. but as far as the assembly goes, because the assembly language is actually tied to the hardware implementation. So if you take a 6502, the reason that there are things like an STA instruction, a store to A instruction, is because there is an A register. There's actually a register in the CPU, in that silicon die, that is labeled A, and when you execute that STA command, it stores that value in that A register. So that instruction wouldn't exist if the hardware didn't have that in it.
And you have that here too.
So I've got an A register, a B
point to
register, a C register. So
where's your registers here?
all right, so let's see. So the A register is, these are the transfer registers here. These are the temporary registers. Mm-hmm. Then you have some control ROMs here. This is what stores.
And are they RAM chips?
These are ROM chips that store the microcode.
But the registers are.
Those are like 7400 series registers. So they're basically 8D flip-flops in a single chip.
Okay, so you're not storing in memory, you're storing in the flip-flops.
Right.
Okay.
So there's a set of flip-flops here that are the T registers, and then you've got the, let's see, there's the A register I think is over here, the B register is over here, and then the C and D registers are over here, and then the ALU, the arithmetic logic unit, is these two chips here. So most of the board here is actually taken up just by registers, because even though each register only holds 8 bits, it's 8 bits that have to know how to do different things. Like, do those 8 bits need to be on the address bus, and they need to be on the data bus, and they need to receive data from the data bus, and they need to receive data from the ALU, do they need to update this clock cycle, should they reset this clock cycle? So all that different behavior is what's controlling what happens inside that register each clock tick. And most of the circuitry here isn't how to store 8 bits of data in a register. That's like one little chip. It's all the other chips to say, this clock cycle, the control logic says you need to reload your data from the data bus, for example. And then there's combinational logic, AND gates, OR gates, multiplexers and stuff that the control logic can signal to say this data needs to go from the data bus, and then this clock cycle, we're going to write that into this register, or we're going to read that data from that register onto the address bus or something. And so you put all those pieces together and you end up with a CPU. Like if you look at the core of a 6502 or a Z80 or an 8088 or something, you're going to find something very similar to this in silicon. It's got a set of registers, it's got an ALU, it's got a program counter, it's got a stack pointer, it's got all those different components. And instead of just taking a design that already existed, as I worked from left to right on this board, I would just say, all right, today's project is stack pointer. How am I going to do that? And I would just come up with a solution, wire it up and see if it works, and then I'd add assembly instructions to my assembler that makes use of that new component on the board.
Nice. Well, this reminds me of, have you seen the 6502 board that was laid out with discrete components?
I haven't seen that, no.
No?
That sounds
you
awesome.
You love it? I saw it up at VCF West a year or two ago.
I've seen projects like that. Like there's a coffee table that's a 555 chip.
Oh,
so
nice.
it's the size of a coffee table, and it's huge discrete components, but it's all the transistors and resistors and stuff that are all scaled up really big, and it's an actual functional 555 that's a coffee table.
So in those small chips is just these components, but shrunk down.
Right.
Which then, my question is, if you look at, I don't remember the numbers. I mean, pick a CPU nowadays, it's got trillion transistors.
Billions and billions.
How many transistors on your CPU? Have you counted?
I have not counted, but each of these individual chips, these 7400 series chips, they don't do much. Like each chip might be, say, 8 D flip-flops, or it might be 4 OR gates. And so, most of those are a dozen transistors or something. It's just not that much.
Right.
The highest transistor count we're going to find in this whole design is going to be in the memories. So the ROMs and the RAM, those have millions of
those
transistors.
aren't typically in the CPU.
Correct.
Unless they've embedded a little bit or something, right?
But we're probably talking on the order of maybe 1,000, 10,000, something on that order of transistors in this whole system.
And with that, you get a working computer brain.
Correct.
Sweet. So, you created the video card first, and then the CPU.
Right.
I do want to say what I am surprised is you did the video card first, or even second, but you never implemented a ding, a buzzer, or
no, I didn't.
No, you didn't have it go like bing, 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 bing.
No sound.
There's no sound yet. No sound yet. Okay. So video card, CPU. What was the next thing on here?
So once I had the CPU functional, so I could actually write normal programs that had branching and were able to execute a program that could load and store and do math and all sorts of stuff. At that point, all I could do was write programs where I could write them to ROM, power the system up, and it would run the program and it would just be done.
Right.
There was no input.
It
there
was
was
hard-coded.
Yeah, so it could have it display something to the screen, but it couldn't take user input. So the next thing I needed to do was peripherals. And in order to do peripherals, you need interrupts, and that is tricky. So with an interrupt, what you have to do is, while the CPU is running, some peripheral in the system needs to be able to signal to the CPU, I need attention. Interrupts the CPU. And when it does that, the CPU has to be able to respond to that interrupt, execute some code out of band from the current program that it's running, and be able to return from that interrupt routine as if nothing had never happened. Which means you have to back up the whole state of the CPU, you have to switch over to that interrupt handler, and then once the interrupt handler runs, you have to go back, restore the state of the CPU, put everything back into the registers the way they were, make sure the ALU registers are back to where they're supposed to be, and then restart the program where it left off. So from the program's perspective, it doesn't think anything happened. It just was running step to step, nothing happened, but your peripheral was able to get serviced, like your keyboard, a keystroke was able to be taken from the keyboard. So I implemented that using some 7400 series parts, and I leveraged the fact that the way I designed the CPU is it's microcoded. So rather than a lot of folks that have done their own homebrew CPUs did what's called single cycle computers, where basically every instruction might be, say, a 24 or 32-bit instruction, but all the control signals for that instruction that say how to get to the next instruction are all embedded in the instruction itself. And that can make a very simple, small, tight computer because a lot of you don't have to worry about control logic. All the control is actually in the assembler. As it writes out those instructions, you're writing the control logic as you go. I went a different direction. I've got these 4 control ROMs on here, and so each of my instructions are microcoded. So when an instruction shows up in the instruction register, so that's an 8-bit value just shows up in that instruction register, that is combined with a 3-bit status from the ALU, so the previous instructions, say it added and it did an overflow or something, those bits are set, and then there's a 4-bit counter that says where you are in the microcode. So that 15-bit assembled value is used as the input to a set of ROMs, so it uses a lookup table, and then each of those ROMs has 8 bits of output, which I put together so I have 32 control signals I can output. So each state of the microcode.
I just want to note there will be a test at the end of the video. I mean, I'm following along, but this is a lot of information, man. So, a couple questions I have. So, just to say on the interrupts, you can do this. You don't want to. You could do this without interrupts, but it's called polling.
Right.
So the CPU has to be like, I'm doing my job. Is there a keyboard stroke? I'm doing my job, but is there a keyboard stroke? Is there something from the serial port? Am I supposed to do something else? And so it has to poll, which is a waste of time.
Yeah,
And
complicated.
And in small systems you can do that. So eventually, back in the 60s, whatever, right, 50s maybe even, they're like, we need a way to interrupt the CPU. And that's where a lot of these boards come from. It's just they needed to do something. I want to interrupt something. But that has its own caveats, right? Where you can't interrupt the CPU indefinitely.
Right.
Because the CPU has work to do.
Correct.
And I wanted to ask, is your CPU refreshing the memory?
No, it doesn't have to do any of that. It's all static RAM, so there's no like DRAM issue where if you're stuck in an interrupt routine too long, you like miss your DRAM refresh and your memory goes corrupt.
So that's another thing is on a lot of computers, the CPU, or the memory management unit or MMU, whatever, a lot of memory chips will just forget what they have, and the hardware reads what's there and then writes it again to refresh it, that little electronic signal. And that's usually put on some chip somewhere, the workload, but you're not doing that. Okay,
no.
Using static RAM. So your CPU can get interrupted and not worry about refreshing the memory.
Right.
And your video board is a subsystem, so it's going to the memory. It doesn't need the CPU to do any of that.
And that's because of the dual port RAM. That's independent of the interrupts. But once I had the interrupts working, that meant the first thing I implemented then was a keyboard. So I actually used I cheated a little bit. I used an @tiny microcontroller, which is funny. This little chip right here, this little 8-pin chip, that's an @tiny 8 running at I think 16 megahertz, which is more powerful than this entire computer, and all it does is run my keyboard.
Yeah. Well, I've got no problem with that. And I'm bringing this up from this. It's like, oh, should your peripheral be smarter than your computer?
Right.
But what a lot of people don't realize is even like on the Atari 8-bits and the Commodores, there is a CPU in the disk drive.
That's right.
So the 1050 disk drive or the Commodore 1540 or... I'm not a Commodore guy. So I think it's like a 6510 that is something like that. A derivative of the 6502 chip in the disk drives.
Yeah.
And they needed that because that is doing a lot of work. That's why a lot of drives were, early on drives were expensive, right? Nonetheless,
you're basically buying a whole other computer that just manages
so you've got
the hard
a computer here and then your computer here.
Yeah.
And in fact, there's an Indus GT over here. You can put a chip in it and run CPM on the disk drive to the Atari computer. So the disk drive has a lot of power in it. So your keyboard controller, or whatever, it has a lot of power.
Yeah.
It just comes down to how much space and money and silicon you want in something. But nowadays, I mean, what was that, $8 part?
Yeah, it was a cheap part. And the idea behind that was
that... And you can't customize it. Like you're doing your thing.
Yeah, and the idea was that by implementing it that way is that instead of taking PS2 scan codes, which are not representative of, say, an ASCII code, they're completely different, and they often have multiple sequences you have to compile together. Well, the microcontroller can handle all that and it just outputs an 8-bit value that says,
okay.
what is the ASCII code of the character that was just struck? And then I can read that from the peripheral much more easily. So I don't have to waste valuable CPU cycles on the main CPU trying to decode a scan code or look up a ASCII code from a scan code or something like that.
Okay, so then you got the PS2 keyboard inputs.
So PS2 keyboard.
No mouse yet.
No mouse, no.
No mouse, okay.
But I also implemented a UART, so that's an 80C52, so it's the same UART that they used back on like the 8088, 8086 computers. And so that's implementing a UART, so I've got an RS-232 port up here that I can communicate with. And then I added this chip here, which is a Dallas real-time clock, which is...
Well, before we get there, for anybody who needs to know, the UART, which... I know the acronym of it, Universal Asynchronous Receiver Transmitter.
Yeah, I think that's right.
Yeah. Is what is used when you're doing serial communications, and what protocol do you implement on that? You're doing RS-232.
Right.
I suppose RS-482, whatever, 485 and all that stuff. So you hooked up a UART, and you're not bit banging the serial port.
Correct.
It actually is driving, but I think you said 1-bit driver.
Yeah, it's a 1-bit serial port, but it gets the job done.
So you got a serial port on there now, which goes to a standard RS-232. And then, funny, you've got the Dallas real-time clock.
That classic Dallas chip that everyone always worries about in their retro computers.
Am I pointing to it?
It's right here.
Yeah,
yep.
right there.
So
if you had an IBM or Cologne or whatever, in the... I don't think the Dallas chip came out till like 92, 93.
Yeah, but it was in a lot of old computers, and it was the one that you were always worried about because when they first came out, they had, I want to say NiCad batteries in them, and they would leak, and it would ruin your board. And so I've seen a lot of videos about retro computing and stuff where people have had to pull their old Dallas chips out, or they had to repair their old Dallas chips because the batteries have died and replace them. And it turns out you can buy brand new ones. Like they're still using a bunch of industrial equipment these days. So you can go on.
So it's not new old stock; it's new stock.
New stock. It's a brand new. It's got lithium cell
right?
in there, so I don't have to worry about leaking. And
is it rechargeable?
It is not rechargeable, but it is. It will last 10, 15 years or something. I don't have to worry about the clock going bad. So as I would if I had gotten like a new old stock.
Right.
So the Dallas chip is good. And then at the bottom board here, so once I ran out of space here, I added a second board to the bottom. And then the main peripherals here is this set over here. That's the extended memory. So this is 32 kilobytes of main memory. So that gets me after, there's part of it that's portioned out for the video memory.
Which is shared for the main memory and the video.
Correct. So there's 8K of that that's used for the video card. There's another 4K of that that's used for buffers and stack and stuff like that. That leaves 20 kilobytes for the actual user space processes to run.
Who needs more than that?
I know, just 20. And so 20K was not going to be enough. And so I added extended memory. So that's a 1 megabyte extended memory.
You're bank switching in and out?
Bank switching. So I've got two 4K banks that can be independently switched. So I could have, say, 8K of contiguous or 4K on two different pages. It's pretty flexible. But that gets me enough memory so that if for example, I'm needing to read some data from disk and it's a large file, like if it's a 500K file, I obviously can't just put that in main memory. I can put that in extended memory. I can page it in there and have enough space for it.
And we'll get to the disk part, so you've got that on there as well. The CPU that you created out of thin air using discrete components is an 8-bit CPU.
That's right.
Right? And which I'm trying to wrap my head on that because I'm like, 6502, 8-bit, that's what it is, the 68,000, 16-bit, You created your own. Why not a 9-bit computer? Could you do a 9-bit computer?
So it's funny you mentioned that because the reason that it was interesting as I went through this Odyssey, building the computer, there were, when Texas Instruments came out with the 7400 series catalog and the 5400 series catalog, these were chips that they made. You could think of them like Lego bricks. Instead of them coming out with a CPU, they came out with a chip that's got OR gates on it, or a chip that's got a shift register, or a chip that's got D flip-flops or JK flip-flops or whatever. And then there was this huge catalog of all these different types of chips. And in the 70s, you had folks like at MIT building the Lisp machines. So they just did basically what I did on a much grander scale, and they implemented Lisp, the programming language, in hardware using 7400 series logic on these giant wireframe wire wrap boards. And they actually have them on display at their library up in Massachusetts. It's really cool. But those use that mechanism. And of course, the MIT Computer Club did a lot of the same stuff where they were just using these chips. But getting to the point about like, why not 9 bits? Why not 10 bits?
Well, we know why not, but why not?
Well, the reason is that when you go through that catalog, there isn't a 9-bit shift register or a 9-bit D flip-flop.
Like you can't
it's
create
8-bit.
one. Come on, look what you did.
I know. Yeah, I'm just going to have to spin up my own fab and I'll start making my own chips.
This is why I don't
right?
get anything done. I'm like, but I could do 9 bits.
Yeah.
Why? Because, right?
It's better than 8, right? 9's bigger than 8.
well, it's the carry bit. It's the whatever.
Right. It's the parity bit.
Yeah. So besides it being an 8-bit CPU, you have a 16-bit address bus.
Right, which is pretty typical for 8-bit systems.
Right.
Like even 8088, 8086, 6502 even has a 16-bit address bus.
Right, because you can't address much with an 8-bit bus.
Correct, yeah, 256 bytes.
Right. So, I can't remember. What do you get with
64K.
64K? Okay.
So 64K of address
16-bit.
space.
Oh, that makes sense. Duh. So, you can address a lot of RAM.
Yeah, so the way I've portioned up that address space is that the bottom 16K of address space is ROM. So that's actually mapped to this chip right here, this program ROM. So that way when the system comes out of reset, it starts at address 0, which is mapped to the ROM. And so that's where the BIOS starts running. It begins executing code from ROM.
Starts at address 0.
Address 000, yeah.
As most computers that I'm familiar with, at least, right? It turns on. It's like, what am I doing first? It's got to go somewhere.
Yeah. So it'll have some sort of reset vector
Yeah.
it goes to. In mine, it's just address 0. I think the 6502, it's like 08000 or something. But so that's the bottom 16K, and then 32K of main memory. That's this chip here, is mapped to the next 32K, and then there's 16K of unmapped space at the top that's used for peripherals. So if you need, as I create peripherals and stuff, I actually just map them into address space, which is, again, the same way that the old 8-bit computers did it. You know, if you're sitting on an old Apple or an old PCXT or something, and you're talking to a peripheral, that's why there's an I/O address, and that's why there's an interrupt associated with it, because what you're literally doing is you're telling the CPU, put this address that isn't in memory on the address bus, and my peripheral is just going to be listening for that address and respond when that address shows up on the address bus. So the keyboard controller, the UART, the Dallas real-time clock, the IDE interface, the extended memory, page registers, those all respond to addresses above main memory, and they're just in that top 16K of address space.
Okay. So we stopped at the Dallas RTC, and what is some of the other subsystems? We were going to touch upon the what would you call it? The offline storage. I mean, you have a hard drive.
Yeah.
But behind here, you also have an SD card. So
That's right.
The system has 2 drives. Drive 0 is the SD card. Drive 1 is the hard drive.
That's right.
Which we have unplugged right now because.
It makes a loud whining noise.
It works, but it lets you know it.
It does let us know. It's an older drive, and I think it might have bearings that are starting to go out. So, but the reason I'm even able to have these devices here is because these chips right here, and surprisingly small, it's just these 2 rows here, implements an IDE controller. So when I first started trying to figure out how I was going to do mass storage, because you have to have some sort of mass storage, I can't put everything in a 16K ROM. There's just not enough space to do anything useful.
And you have to burn that ROM every time.
Very frustrating every time you change something.
How long did you do that for?
For a long time. It's only just recently that I've added the IDE stuff. And so
where's your burner?
It's right here. I actually had to make my own burner from scratch. And so that's all done using kind of my old style point-to-point soldering. This uses an MSP 430 microcontroller and a TTL UART, and then I wrote a Python program to talk to it. But that's how I was burning all my ROMs. So every time I'd make a code change. And so when I got to the point where I was able to start implementing some sort of mass storage, I had lots of ideas. Like there are modern chips that have like NOR flash in the chip, like a megabyte of NOR flash that you can access just using an 8-bit direct interface. I could just wire that right into the address space and say, all right, well, that's my mass storage. And I thought about, well, then how do I get data like off my laptop into that? Like I need some way to removable mass storage.
Right.
And so I started thinking, and I did some research, and it turns out that the IDE, the ATA protocol, that it was used in computers like all the way from like the 286, I think, all the way up to like the Pentiums. They were still using IDE, ATA, some
Before
flavor of it.
SATA.
Yeah, before SATA it's a magnificently simple and easy to implement protocol, which shouldn't be surprising because they were able to do it on such old original hardware. But when I finally read about it, it kind of clicked. I was like, oh, that's not that big a job. Like I could actually make an IDE interface, and then once you have an IDE interface, suddenly the options get much bigger because anything that can speak ATA, which can be SD card readers or hard drives or all sorts of other stuff, I can just plug in and then my computer can talk to them. And so that's why I decided to implement an IDE interface instead of something like Serial or SPIO or NOR Flash or something like that.
I find everything is like, how do planes fly? Right? Like magic on the wings. So that's how I look at the computers. Something I'm not familiar with, I'm like, oh, there's some kind of magic behind there. But if you get into the tech docs and stuff, sometimes you realize this is really simple stuff. They just put a lot of time and effort into it, and the new tech and the new idea of how to do it, how do we simplify it, what do we need for the systems to support them, and they put those commands in there.
Right.
And often it's a different kind of interface, it's a different kind of like language talking protocol, and a different purpose, like a keyboard from a hard drive. But ultimately, if you read the tech docs, you could work with this stuff.
Yeah, for sure.
Which is, again, we're going to keep bringing up Ben Eater. That's what he does. He's like, here you go, we're going to make this work. And all of a sudden he's got computers with blinking lights and stuff. And you're like, oh my God, I did that myself.
Right.
Right.
And it's just so amazing that, that's one of the things that I've really enjoyed about working on this, which is discovering, sometimes accidentally, how things were implemented back in the day.
Sorry.
And how elegant a lot of those implementations were. So elegant in a lot of ways that you can actually stumble on those same solutions by simply trying to do the same thing again. So like when I was implementing the video card, for example.
Right, you were telling me about that.
So I was laboriously going through, because I had designed this thing, again, I didn't base it on an existing video card design. I was just kind of doing it on my own. And I knew I wanted it to be a character-based system using ASCII codes, code page 437 from the DOS days. That was my goal. And to do that, I needed a font ROM. I needed a character ROM. And so I wrote some software to actually compile my own font ROM based on a set of glyphs that I made myself. Until I realized, I went to int10h.com or .org or something. It's an archive where they keep all these old like IBM CGA video cards and stuff. They've taken the ROMs off of those and saved them. Well, it turns out that the format that they used back on the old IBM and Commodore and all these old video cards, these character-based video cards, it's the exact same format that I came up with on my own. Completely unrelated, but I was literally able to just take those legacy archived ROMs off of int10h, burn them onto my font ROM, and it just worked right out of the box. And so I could stop. I could stop the work on like laboriously creating all my own glyphs and my own font and just use the ones that were already designed by IBM and Commodore and all these other companies back in the day.
Cool. And we're going to show some of that later when we get into making this do things. So where did we leave off? You were talking about the storage,
yeah.
Right? And so you can access, can you take out the SD card or will it mess up the system?
No, it works fine. I mean, it doesn't work. So if you swap cards while the system's on, I still haven't figured out how to get it to notice that it's a new card and remount it.
There's a refresh line or something.
It locks up the system. And I think that this particular SD card reader, this SD to IDE interface, doesn't properly respect that reset signal. And so you end up just having to reset the computer, bink, when it...
You have a reset button?
I do have a reset button. It doesn't have a speaker, but it does have a reset button.
Right. Okay, so we got the storage system. What's any? I've lost track. Any
That's
other
it.
subsystems?
That's it right now. But you see, there's a bunch of board space left.
Right.
So I've got some ideas of what I want to do next, and I've actually spoken to some of the attendees at VCF about this. I actually asked as people walked up to my booth, and I said, well, I've got all this extra space. What do you think should be on the Odyssey next? What should I build? The number one thing that I got back from folks at VCF was you got to put a sound card. And you even mentioned the same thing. Like, it doesn't make sound. It needs a sound card. And so I've thought about using, there's the like the OPL3, like the Yamaha chip that was on the Sound Blaster. Well, that's an 8-bit accessible card. Chip, and so I could integrate one of those into part of the address space,
or a Pokey chip. I'm just saying, Atari Pokey chip. I mean,
possibly, yeah.
I mean, I'd vote for that.
Okay, but yeah, that's certainly coming up. Is I want to add a sound chip, and I'd also like to add a more sophisticated timer. So right now I'm just using the Watchdog timer in the Dallas chip, which is useful. Because I can tell it, signal the Watchdog, and then, I don't know, 10 milliseconds later, fire an interrupt. And that way I can do things out of band. I can be doing some processing, maybe count some cycles or something, and then when the interrupt fires, I can do something like refresh the screen. And so I can refresh it exactly 30 frames a second or exactly 10 frames a second, regardless of what the clock speed is. And that's really useful, but I only have one. I've got one interrupt that I can control right now. And if you're trying to do something like write a game, or even trying to do something more sophisticated, like if I even wanted to do like asynchronous file access, like you need additional timers to do timeouts and stuff. And so I want to add some custom logic that lets me add 2 or 3 more timers that I can program for certain amounts of time and then trigger different interrupts. So that'll be some extra space. The sound card I talked about. And then I'm thinking about also adding an LCD display. So right now this is hooked up over VGA.
Yeah.
And of course everything can happen over VGA, but all the homebrew computers I've ever seen have all had a little LCD status display in the front that tells you, the current clock speed and the current time, and then as you're doing stuff.
Which you have commands to show.
Exactly.
We're going to get into that
and so,
as well.
I just think it would be fun to not have to be dependent entirely on that VGA display. It'd be kind of nice.
Right.
It's kind of reminiscent of like the old SPARC machines. Like you'd boot up these old SPARC servers and they had a little LCD display in the front, and so you turn it on and it would actually help you see that it was booting up and getting through its power on self-test, and then the serial port would light up and you'd actually start to interact with it. And so, I don't know, I think it'd be fun to add a little LCD display to it as well that's addressable. Cool.
And you got a lot of choices nowadays, so that's... Yeah. Okay, so... we're going to get into, you've got that hooked up to the monitor. We're recording that over here, and we'll put that up on the display of what we're doing. But before, we did touch upon the wire wrapping.
Yes.
But I'd like to see your tools. For people who don't know wire wrap. So, do you have...
Yep, so this is wire wrapping wire. So, that's... This is what it looks like right here. You can see
30 gauge, right?
Yeah, it's a 30 gauge wire. It's got a very thin polymer insulation called Kynar. In fact, if you're thinking about doing wire wrap, only get Kynar wire. Don't get the silicone. There's a bunch of different kinds, but Kynar is always the best.
Okay, and it's basically solid
core.
Basically, it is solid core, 30 gauge.
Silver coated wire.
So that it will carry a signal and also bend when you literally wrap it around
Correct.
the pin.
And that's what this tool is for. So this is a wire wrapping tool. So there are fancier ones. This is kind of a simple one, but you strip the wire, you stick it in the end here. There's a little notch on the side that you send the stripped wire, and then you just push this down on the pin and you spin it, and it wraps the wire around the post.
Which is all on the back side here.
Right, and then I've got...
And again, we'll have a photo up here.
And then I've got a set of wire strippers that go down to 30 gauge to makes it easier.
You don't just use your teeth?
Yeah, no. There's a lot of people that do, and actually this actually comes in the back of the tool. It actually has a little stripper, but I don't like using it. It's you can see it's a little chunk of brass. It's a little hard to use, and those have nice big handles. Yeah,
for any of the should we say younger viewers, at least talking about myself here, I used to just pull wires any job, any hacking thing I did since teenage, I was like,
Yep, just in your teeth.
Somewhere in my 30s, my mouth was like, I don't like that anymore.
Yeah.
just don't do that again, Steve.
Well, and with wire wrapping, it's actually very important that you don't do that.
Because you're making it all wet.
Well, no, it's not that. It's that with wire wrapping, it's really important that you only strip the insulation off, that you cannot nick the wire.
Oh, my teeth are not that. not that sharp.
But when you get a good set of strippers, they have a flat spot so that when you squeeze all the way down, it does not clamp all the way down on the wire, so that you get a good clean strip. And I've had it happen a few times. If you get a bad strip where you nick the wire, when you try to wrap it, the wire just breaks and it comes right off. And so you have to be very careful with that. The only other tools that I use are these. So I don't use a whole lot of tools. I use a set of cutters to cut the wire. I've got a pair of tweezers that can kind of help me work in tight spaces, and a little flathead screwdriver that I use to kind of move wires around and stuff on the board where my fingers can't get.
And that's it. You can get automatic tools, but you don't go that.
Yeah,
you're OG.
I don't know. And what's funny is I talked to Bill Hurd at VCF, which is a great thing. If you ever get to go to VCF, you get to meet famous people like that. But he actually got to see the Odyssey, and he gave me some feedback. In fact, that's why the power is run this way. His feedback to me was, this all looks great. I love the way you ran the address buses and stuff, but you don't have your power routed correctly. And he gave me some pointers on how to route my power better. So
it doesn't interrupt.
Well, it's just that you get even amounts of power across the whole board. I was feeding all the power in from up here, and it was having to go from board to board to board.
Yeah.
And so he suggested distributing the power out so you have a good solid power bus, and you don't have to ever worry about your power again. And
cool. Let's go ahead and get this system. Well, it's already fired up, but let's get it on the screen, and let's do some commands.
Yeah.
So I'll get that going in a moment here.
Yeah. So let's go ahead and we'll put it on here. So what I want to show here is I'm gonna hold the reset signal. So what that's going to do is, as I power this up, everything's going to be in its original state. And what you're going to find is you get gibberish.
Nice.
Because right now, video memory, that's right up here, has no data in it. And it's because
I would build a computer just to do that.
Yeah.
You definitely need music for that.
So when I let go of the reset signal, it's going to now boot the system. It's going to, all of the registers are going to get reset to 0. The program counter is going to reset to 0. And then it's going to begin executing code from the program ROM here at address 0. And then you're going to get this. So it actually starts executing by booting into what I call Odyssey OS. And it starts...
Which is, to me, is hilarious. It just looks like a PC's booting up.
Yeah, I mean, it's based on that. Again, I grew up in the, using computers from the early 90s. And so when I was writing my own operating system, of course I'm going to write it to behave the same way that my old computers did, because it has a memory check at the beginning, and you see your, the initialization stuff happening. You see some diagnostic data as it boots up. So this all was very cathartic, I guess, for me to get to relive some of my old computer days, even just writing my own operating system.
My first computer booted up and gave you memo pad.
Yeah, that's right, because it would just boot and just go directly to the prompt.
Right. There was, I guess it went to the direct address to run memo pad.
Yeah.
Because there's no software in it. But anyways, okay, so Paul, let's take this for a run.
All right.
You've now everything on here you coded.
That's right.
Right. This isn't, you're not like, I downloaded the whatever command and I'm running that one. You created the CPU, you created the instruction set, and you created the utility. Well, the background stuff. You got like housekeeping happening.
Oh yeah. There's a memory allocator. There's an interrupt handling routines. There's ATA management routines. There's UART management routines. All that stuff.
File storage, the ATA stuff, and even the directory command, which you chose to use dir.
Right.
Because again, it's just common knowledge, right? dir or ls, right, for Linux.
Yeah, if it was LX for Linux, but what's kind of interesting if you're just run dir. So what that actually did, what's funny is that it looks simple. It's like, oh, well, of course, you just did dir, you got the list of...
Yeah.
But what that had to do to work is it had to interface with the IDE controller. It had to find and parse all the FAT16 file system metadata. So it had to find out what large block addressing LBA blocks contained things like the file allocation table and the root directory. It then had to go tell the IDE controller, go fetch me these sectors given these LBA addresses for the root directory, parse the data that came back from that root directory in these 32-byte segments that are each directory entries, decode what's in those 32 bytes, and then print them on the screen as something readable. So it's just been mind-boggling going through how many layers of abstraction we live on today. You imagine like a modern Windows or Apple or Linux computer, and you think, oh, well, I just Control X and pop a shell. And you just think about the billions of instructions it had to do just to present you a blinking cursor. And of course, I'm having to do all this from scratch myself. And so, of course, it's not graphical. It's not a multi-user system. It's not all this other stuff. But just getting to the point where I typed dir and I saw a directory listing was an amazing day. Like,
right.
I had to bring my wife over and, oh, take a look, I can do directories. So it's pretty amazing
this
stuff.
This is where you danced around the
house. Well, the Hello
We-
World as well.
Oh, right, the Hello World. Too.
Yeah.
And then let alone if you went to load something, now you got to go back out and load it into memory.
Exactly.
And then execute it.
And which brings us to another good point. So you see that file there, system.od. And if I cd to the sys directory, you'll see there's a bunch of other ODY files. Like, what is an OD? Well, that's an Odyssey executable, because I had to come up with my own executable format that works with my operating system. What's that?
Anything else use the extension OD?
Not that I'm aware of.
Okay, good.
But I picked it because I didn't want it to be like .exe or .com.
Right.
Because that could be confused for a DOS executable.
And then you'd have to write a subroutine that would come up and say, this is not a Windows program, right? Can't run that on this system. You're not authorized.
But I think it helps drive the point home that, like, the fact that I'm running commands that aren't .exes or .coms. Like, it's easy to look at something and it looks familiar. This looks kind of like DOS. And so anyone that's familiar with retro computing and has run DOS 622 or something before, or run CPM, says, oh yeah, well, that, of course, that looks just like CPM. So you're just running CPM on this, right? Like, no, it looks like it, but it's not. It's a completely separate thing all from scratch. Are you going to get
sued by the CPM consortium for the look and feel here?
Hope not.
The Odyssey versus the recreation or re-earthing of digital research.
Yeah.
I don't know, whatever. Okay, so we've got commands here. You've shown, taken a look at them, and well, let's look at the malloc.
Yeah, so one of the things I had to do early on was to be able to allocate memory. So if you look at something like an Atari game console, 2600, or Famicom or a Nintendo NES, those, they might have had a memory allocator, but they didn't really need them because they ran one program. The cartridge contained the one program it ran, and so whatever memory was in the console was used by that program. So like all the memory addresses could be static. So anything that it did, like the number of lives you had was always at the same memory address because that's the only thing that was running in that program. When you try to move something toward being a general purpose computer with an operating system, one of the things you need is a memory allocator so that you can tell the operating system, I'm a program, I don't know what's in memory right now, but I know I need 2 kilobytes of memory that I can put an array in. And then it can return back an address to say, you can use this memory, no one else is using it. And then the operating system keeps track of who's using memory and what's free and what's allocated. So I implemented all that in the operating system, and then I wrote a utility called malloc that, so you can run like this, and it'll tell you the different ways you can call it. So you can, I wrote it mostly for diagnostic purposes, but you can allocate segments, allocate blocks, free that memory, or list current allocations. So if I do malloc L to list, it will show that there are 1280 current allocatable blocks, of which 946 are free, 33 or 4 are allocated, and it gives you the addresses of all the currently allocated memory. So if we go look at what's in some of that memory, I've got a utility called hexdump that is just a memory dumper. So I can run hexdump, and let's say I want to look at, say that first one, that OX99BO, and I want to look at the first 128 bytes, and then it will print out And I'm getting a little bit of glitching here, and that's probably because the font ROM is getting a little loose. It sometimes does that. So
interesting.
sometimes there's some loose connections. But this demonstrates a couple interesting things. One, color. So that was a big thing for me, is I wanted to make sure the video card could do color. And so we can see here we're using color, and I'm using that color to make this more readable, so that the rows and the columns are using slightly different colors, so that it's easy to decode what's on the right there and translate it to what's on the left. And so what we can see here is those first 3 bytes are ODY, which is the header of an OD executable. So what we can see here is that in-memory address 99B0, a total of 64 16-byte blocks, is taken up by a program in memory. And it's actually, what's funny is that when I ran malloc L, that 99B0 was actually the malloc command itself in memory. That's what we were looking at.
Nice.
So that's one of the commands that I can run here is hexdump to look at memory. And I can also use peek and poke, which is a familiar command from, say, a Commodore.
Right.
So if I say clear the screen here, and I can do directory again, we can see the way the memory is mapped out. The character memory in the video card starts at address 4000. So if I do peek 4000, and I want to look at the first, 16 bytes, you can see that, as you can imagine, right there, you can see 0:/sys/whatever, and then I can poke into that memory. So poke OX 4000. I can poke some hex value into that, and you can see at the top of the screen that 0 changed to a $, because I just poked that value just like you would.
That's just in the video buffer.
Yeah, that's just in the video memory, which
so
is of course shared with main
instructions
memory.
that ran to put that there wasn't changed.
Correct.
So just for anybody wondering.
Yeah.
Additionally, I wanted to ask, obviously this is not a multitasking operating system.
No,
so
not at all.
Single tasking.
Yeah.
Okay.
So it's very similar from an architecture perspective, like from the operating system. You would think of it as like real mode in DOS or something. So when they made that big change with the 386, they added virtual memory and paging, and that's what gave you the ability to be multi-user. Well, this is more like an 8086 or an 8286 that was running in real mode, so it didn't have virtual memory. So there is no, I can't bank switch between like ring 0 and ring 1 or something and have the kernel running in one space and a user process in another.
Okay. The next command is colors.
Yeah. So again, highlighting the fact that this does do colors. This was another test command I wrote that shows all 64 colors that the video card can display. And the weird characters you're seeing there is the routines that I wrote for handling terminal output. So when a program writes to the terminal, it can insert these @x commands into the output stream, and it will set the colors so that you don't have to manipulate all the bits and bytes by the program. So it's a routine similar to what the IBM BIOS did. So the IBM BIOS had routines that would handle terminal output, and so I've done the same thing. So the BIOS ROM contains the terminal output command, and programs don't have to worry about it. They can just say, put a string into memory, put the address of that string into a register, and then call some function from the ROM, and then the ROM handles printing it out, and part of the function is if it sees these special escape codes, it will color the text as it prints it out.
Okay, cool. I like seeing the color on there. You've got some other stuff. Let's do, was it MEMPA or FPS?
Oh, yeah, FPS.
The flashy thing.
Yeah. So
make it flash.
Yeah, so one of the things that I wanted to be able to do down the road is to use this to write some games, perhaps. And so for that, you need a reasonably high refresh rate. And so I wanted to test how fast I could refresh the screen using different system calls. So I've got different instructions for doing things like writing a specific byte to memory many times. So like write a null character to the next 2K of memory, like really fast. And so when I run this little command here called FPS, it's going to start by doing that, where it just puts a single character across the whole display as fast as it can. And then it's going to try something where it copies memory from one memory location to another into the video card, and that's going to be the second method. And then the third method is writing code to actually generate the output.
Like a bit blocking.
Yeah, like bit banging kind of at the end.
So don't do it yet. Don't do it.
Okay.
I just want to note, again, you created your own CPU. running at 2 megahertz
Right.
in your own video card, and this is what it does.
Yes.
Go for it.
All right. So FPS here. So there's the just test patterns showing what it can do.
Yeah, that was pretty fast.
Yeah, and you can see
that should be great for games.
Yeah, I mean, you can see the fastest one, which is the memfill. It's the same routine used for like clearing the screen and stuff. 220 something frames a second, which is really quick. And even using the mem copy method, which is you would use for like a double buffering strategy, where you have procedural code that's filling up, say, a block of extended memory with the next frame, and then you do a quick refresh. You basically pull all that out of memory, copy it into video memory all at once, and I can do that at just over 60 frames a second.
I wonder, I don't know if it's the best choice, but if you grab like the Blitter chip from an Atari ST,
Yeah.
I wonder if you can implement that in there.
I'm sure
if you
I could.
even wanted to, but
it would be, it would be a whole re-architect. And I do actually want to redo this video card. There's a bunch of places.
of course you do, right?
Yeah,
Once you've done, you're like, I can make that better.
I found so many mistakes of how I did it. Like it doesn't support background colors, which was, I don't know why I didn't do that, but I never implemented. It's only got black as a background
You
color.
can have any background color you want, as long as it's black.
As long as it's black,
Yes.
exactly.
Yes. Let's check out the random number generator.
Yeah.
You implemented that.
So the random number generator is just a pseudo-random generator. It's about 20 lines of code. It uses a seed that's just a address in main memory that is fixed. And so when the system boots up, it doesn't reset it to 0. So it's going to be at whatever random state that
Right.
memory was.
The address number isn't fixed. When it goes to that fixed address,
correct. The
it'll
value.
I don't want to use the word random. It'll find a leftover signal of electronic garbage
Right.
that was just in there when you turned on the chip.
Exactly.
But I quizzed you, and you're not sure. It could be the same number.
It could be the same every time, as far as I know, because I suspect that this memory chip probably doesn't, when it powers off, doesn't come back completely random. It comes up probably with a reasonably static pattern. But at any rate, I use that as a random seed.
But as the coder of the system, you can augment that if you discover that's an issue.
And I could add like a seed random. In fact, there is a random seed command. I just don't use this here. But here, like, I generate 10 random numbers between 100, 1 and 100. And I can run it again. You'll see that you get different random numbers each time. So,
Okay.
random number generator.
Cool. You got to have that. Definitely for games.
Yep.
The ASCII character set. So let's, the ASCII command. So you have bitmapped into the video card
Right.
character set, which you have to wrap your head around this. The video doesn't just draw, like, hey, let me draw everything. I mean, it does. But it doesn't know how to draw the letter C, right? It's got to be told, and so it needs that somewhere. And you don't have instructions that draw the C. You have an instruction that says the bitmap for C exists somewhere. Go grab it. And so that is a set, and you have that bank switchable.
Correct.
Yeah. So this is the character set that the system's currently using, and in real time, if you switch it right now.
Yeah. So I could actually go here, and I can flip these dip switches. So if I flip this switch here, for example, that's going to put me onto a different font, which is old-timey, Old English font.
Yeah. And I find it fun that it does it in real time. It doesn't have to redraw.
Exactly, because it's not, like you said, it's not the computer drawing the pixels on the screen. All the computer has done is write the letter C into a particular region of memory, and the video card encounters that 8-bit ASCII code of C, and then looks up that value in the font ROM and says, well, what pixels do I need to draw on this row to make that look like a C?
Right.
And so you can change that out by flipping those dip switches and live change what the display looks like. And I will say for the viewers watching this, as we said, we're running this through a video capture system, and it's converting the original signal to a HD signal over HDMI, which means everything's getting stretched horizontally. So when I use this normally, I've got a 4x3 ratio display that makes everything look correct. So this looks a little wonky. You know, for those viewers out there, you probably see this stretched a little bit wide.
Yeah, it's going through like 4 systems here.
Yeah.
If you had your, you've got your 4x3 monitor over here, it would look fine. But I wanted to record the video, and hence we got this.
But the reason that it's like this, so the reason, you might wonder, why, oh why would you go through the effort of putting dip switches on here instead of just doing it once and having it be done?
Yeah.
And the reason is that because this is a character display, so right now, it can display 256 different glyphs. That's what this ASCII command shows, is those are the 256 glyphs it knows how to show. And if I wanted to make a game, well, I'd love to be able to have some sprites. So a character sprite or a gun sprite or a tree sprite or something like that. Well, this video card's not sophisticated enough to have sprites. It's not a graphical video card. It's a text display. So I left enough room in the design for 16 pages of font ROM so that when I was going to start playing, say, Tetris, I would maybe run Tetris, and of course I haven't done this yet, I theoretically would do this. The program would come up and say, all right, set your dip switches to 1001, and then that's going to align with the Tetris character set. So instead of having the character A, for example, it would have the block with the line through the middle. And it's,
just like all the graphic characters on the original machines. So, even the IBM had the graphic characters.
And so I could, instead of being locked into just the code page 437 glyphs for drawing the game, I could have some of those higher numbered glyphs be the sprites for my game. And so, of course, if I didn't flip the switch, Tetris would still run fine. It would just have, an inye, some sort of weird character instead of the character glyph or something. But by adding that set of dip switches and making the font ROM pageable, not only can I just select different fonts on the fly, which is kind of fun, it does mean later on as I do more development, I can potentially have it appear to be a more graphical experience, even though it's just a character display.
Right. Okay. Did we do mem test?
We did not do mem test yet.
But it does destroy the memory.
It does destroy the memory, which is kind of funny that a mem test...
Have you built a command that just makes this melt?
I have not.
You can do it once.
There is no halt and catch fire command, no.
There you go. FPS.
We just did that one.
Oh, we did?
Yeah.
Was I here for that?
Yes.
Okay.
That was the flashy one.
Oh, right. Okay, so the mem test, let's take a look at that.
So I can run the mem test, and what it actually does is test the extended memory. So the main memory is up here. I don't test that because it's main memory.
Active.
If something goes wrong, I would know it immediately. But the extended memory is down here. That's these 2 chips. And so if these 2 chips, if there's something wrong, either with the bus connection here, or here, or here, or here, there's a lot of places where something might go wrong. And so the mem test is a way to absolutely make sure that all that connectivity is good. So when I run this, it's going to destroy all the data in extended memory, which is actually where we store all of the malloc data, which means that's why it's destructive. So it's going to run this, and it's running the extended memory test. It will complete. It should say that everything's good at the end, but after it finishes, I have to reboot because it will have destroyed all the malloc data.
Right.
But you can see it's doing it. I actually looked this up. I did some research and found the algorithm that the IBM PC used to do its memory test when you powered it on, and I've implemented that same algorithm here. So there.
It's all good.
It all passed. Everything looked good. But now I have to reboot it because all the malloc data is gone.
Right.
So come back and start over.
Well, you should have it just stop and be like, reboot your system now.
Yeah, I should.
Yeah.
I wrote that mem test command before I actually rewrote the malloc memory management stuff to use extended memory. So when I used to run mem test, there was nothing in extended memory it could destroy. But now the first page in extended memory is actually the memory allocation table. So it ends up wiping that out.
Well, as far as testing, I want to mention, in your earlier days, you really had to rely on a logic analyzer.
That's right.
And you've got all these points on the board.
Yeah, I got all these headers at the top here that fortunately were built into this wire wrap board when I bought it. But it allowed me to expose registers, control signals up to those headers so that I didn't have to go connect the octopus, one little wire at a time from the logic analyzer. I could just take the big 16-bit dongle and just plug it right onto there and get all 16 wires hooked up every time.
16, but your logic analyzer
Can do 192.
Yeah, which Paul, $100
Yeah.
10 years ago.
It was ridiculous.
HP logic analyzer with all the boards for 192. That's sweet.
Yeah, 250 megahertz logic analysis with 192 connections, and the Hewlett-Packard software, which itself is very valuable because it lets you do really sophisticated
if-then logic,
and timing stuff. You could do external triggering. Like I could set it up so that when a certain instruction is encountered or when a certain logic setup is encountered, it actually sends an external trigger over a BNC wire to my oscilloscope, which then triggers, and I can actually do a high-res trace of signals if the timing capture isn't fast enough on the analyzer itself. So I could not have made this without that logic analyzer.
Yeah, so if you're looking at doing something like this and you get this big, you really need to see everything.
Yeah, and I probably could have made do with a smaller one, like one of those Soleil Logic 16-bit or 32-bit logic analyzers. You don't need a giant HP 16500 mainframe. I just happened to get one for really cheap. So if anyone out there is thinking, oh, I want to try this, but what equipment do I need? Don't necessarily go looking for the biggest logic analyzer you can find. 8, 16, 32 bits should be sufficient to debug most of the problems you might run into.
Right, but now you've gotten to a point where you can debug, you can update the software on the SD card.
Correct.
From your modern laptop. And which I guess would be your IDE system,
right?
Integrated development environment.
Correct.
On your MacBook there, or is that
Linux framework? Framework.
And then pop it in here and run and test things.
Exactly.
Right, and you don't need the logic analyzer and so much anymore.
And I've actually written now that I can do that sort of stuff. The CPU is stable enough now that I rarely need to actually hook up the logic analyzer, and I've actually written debugging utilities in the firmware. So now the BIOS actually contains some tracing instructions. So in my programs, if something's misbehaving, I can just insert some trace statements and it will actually print out like the register status and stuff on the screen. So I can actually do the debugging live on screen. I don't have to go hook up extra wires and stuff unless it's actually a logic problem in the wiring. Like there's a timing problem, or there's a loose wire or a missing wire or something where the wires are actually just not getting the signal where they're supposed to be. As long as the CPU is running okay, I can actually do most of the debugging with the assembly equivalent of like print statements being inserted in my program.
Nice, nice. Have you thought about creating an emulator for this?
I have actually. There's a lot of people out there. Like I saw a video recently of someone that took and they had built a homebrew computer around a 4004 chip, which is like the oldest microprocessor from Intel.
That's like chip 1, isn't it?
Yeah, it's like the microprocessor, right?
With a calculator was it?
Yeah, it was for a calculator, but it's a 4-bit microprocessor, and he built a working computer similar to this around it. Used a serial interface, so it didn't have a video card or anything, but he made it run Linux, which is objectively impossible because Linux doesn't run on a 4-bit processor, and B, requires things like a memory manager and all that other stuff. So the way he did it was that he wrote a MIPS emulator in 4004 assembly. So he wrote a MIPS emulator so he could basically boot up an emulator that would behave like a MIPS microprocessor, and then on that started running the MIPS version of Linux on top of that.
Nice.
And he made it work. So it is...
And then Doom on top of that.
I'm sure, yeah.
Yeah.
I mean, what's funny is the video actually ran, so he had a clock, and it took like 3 days or something to boot Linux up on that system. So, but I could do something similar. I could eventually perhaps write a probably MIPS emulator, and then there's a lot of software you can target at MIPS. You can compile with MIPS as a target instruction set, and then you can just take that compiled code, run it under the MIPS emulator. It would probably run really slow, but it would run, and we could run pretty much anything we wanted that's compilable to MIPS.
Oh. My question was the other way around. Have you thought about writing an emulator like on your modern system that emulates this?
Yes, and I did get asked that a lot at VCF. Like people really, really wanted to be able to go to a website, like to go to my website and be able to write their own Odyssey programs and then run them on an emulator. And I have thought about it, and it would make software development faster because I wouldn't have to keep
have
moving SD cards.
crowdsourcing. People would be able to help.
So maybe someday I will. It's a reasonably simple architecture.
Project, right?
The main issue with writing an emulator is not so much the CPU part of it. It's the peripherals. Like how do you properly simulate the Dallas chip? How do you properly simulate interrupts? How do you properly simulate my specific homegrown keyboard controller? So getting some of those things to work correctly in an emulated environment where the code still works on the real machine is where I kind of got stuck. Yeah. And so I never really got past the design stage, but it is in my mind because I think it would be really fun, especially as we get down the road and I keep bringing this to VCF, each year, there's probably going to be more people that might be interested in participating, and this might become maybe it's still a one, like no one's ever going to build another one of these, but it'd be fun.
Oh, don't say that, because you just ruined it right there. Yeah. Somebody's going to work on it now.
Yeah, I'm sure they will. But it'd be fun to have the community working with me to write cool software and stuff and showcase it at VCF and stuff.
Yeah, it's cool. So we have you have I don't want to say limited software, but it's you. You're a one-man operation. You're writing all this code. So these are some of the main programs you've written. You got some other utility things which aren't so fun to watch, but they're heavily needed. But the last thing, and I'm an RS-232 kind of guy. I love, that was the early communications. Everything was like, you got RS-232 or 45, whatever. You can connect stuff together.
Right.
And you've got that. So you've got a UART and right there, and you've got it linked to your Linux laptop.
That's right. So,
and what can we do with it?
So right now, you can see here, there's the UART here, and that's wired up through a MAX 202 to the RS-232 port. And then I've got a serial cable going here to an RS-232 adapter, which is hooked up to USB. And then on my laptop, which is running Linux, this has a Getty, so that's a serial TTY, teletype interface. So it's essentially it's presenting a multi-user login port over serial. So it's basically waiting for someone to log in, just like the old mainframes that you'd connect over a serial terminal and you'd get a login prompt over serial and you have multiple users using it. That's doing the same thing here, but with modern Linux over a USB serial port. So if we switch back over to the terminal here, so first I can run, so you notice that when it booted up, it does note that the UART was initialized at 9600 BPS. Okay. So at 9600 baud is set up, and that's how the computer is set up right now to listen. So now if I just run console, there it goes.
Okay, cool.
So now we're getting a login, and I can log in here, and we can see...
And that's logging into your Linux
laptop.
Running on the laptop.
So
none of that is running on the Odyssey.
Correct. So what the Odyssey is doing here is essentially emulating something like a VT220 dumb terminal that would just be a serial terminal. But if you opened up one of those old VT220s, just like we were talking about earlier with hard drives, like they had their own CPUs and stuff in them, like a VT220 was a computer in its own right. Like it had a character ROM and all that stuff, and it had a bunch of chips in there, but that's what this is doing. So I've written software using the general purpose Odyssey CPU to interface with an external system using the VT220 protocol, which it can talk over serial to a Linux box. And so now I can go here and I can just interact with my computer. And you can see there's some characters that don't get printed correctly because I haven't quite finished with all the VT220 ANSI escape codes and stuff, but it does work. I mean, clearly I'm able to print stuff out here and interact with my laptop.
What I'm finding interesting is, because you've, I don't know how long this video will be, 45 minutes, an hour and a half, who knows. But we've been here for a number of hours, setting up and testing and playing with. And what I'm realizing is your console program is the first program you've run, or the only program you're running, that doesn't just do something and go back to the prompt.
Right.
It's still resident in memory, it's still running, it still has control. Cool.
So obviously just a bunch of output here. I'm just running a PS command. But yeah, so that's pretty much what it can do now. There's still a lot more that I want to be able to do. And so at future VCF SoCal, we'll see the Odyssey showcased with each year, hopefully new features. People can come take a look.
That's cool. Well, thanks a lot, Paul, for coming
Yeah.
up from San Diego. It's a like 3-hour round trip.
About an hour and a half, a 3-hour round trip. Yeah.
Yep. 3-hour round trip. So again, Paul, we'll have the website up here on the screen somewhere and in the description. So Paul, you'll have this, hopefully you'll make VCF SoCal this coming February 2026. If not, obviously it's online. You've got the GitHub page and your a separate web page as well, right?
Yep.
Yep.
WireWrapOdyssey.com.
And we got lots of, well, you've got lots of pictures and data up there. And I think I saw you spoke at VCF SoCal in 2024.
That's right.
And I think in that video you were saying that your GitHub isn't set up to be like, here's how you do it to recreate it. Yeah, because this is still a work in progress. Correct me if I'm wrong, you are barely keeping up with yourself in your head with this.
Yeah.
I can imagine.
Exactly.
So you've got scribbled notes and updates and things in the margins and all those notes on the GitHub page. So it's more of a informational, your journey through this.
Yeah, it's just a place to archive it. You know, what I'm sure there's people out there that are interested and they want to follow along.
Yeah.
And they're welcome to do so. I just don't want to give the mistaken impression that if you go to my GitHub page or you go to my website that you're going to find like a kit you can download to go build one of these or something.
Are you going to design a 3D printed case for this?
I actually like it this way. I think this is it shows off nicely on the acrylic backboard because you can see through and see the wire wraps on the other side. And
Nice. Well, Paul, thanks again, and thanks for watching. Hope you guys enjoyed it. Leave comments down below for Paul. You'll probably check.
I'll be checking it out.
Yeah, because I'm not going to be able to answer these questions. So again, thanks a lot, and this was a lot of fun. We'll see you next time.